Okay, so now we come to our actual topic, the radioactivity. So now what is this radioactivity? Who have discovered it? Okay. So first, Henry Becquerel discovered this phenomenon of radioactivity in the year 1896. Okay, so after a series of experiments, he concluded that the uranium and its salt emit some rays, okay, a kind of radiation which can passes through even with the black papers, glass, or even wood covering, the photographic plates, and also it affects. Okay, so now they have come up with this is something very different. So this cannot be a surface phenomenon. Okay, so it has to be a something nuclear phenomenon. So they have concluded that the radioactivity is not a surface phenomenon as it can penetrate. It is a random nuclear phenomenon. Phenomenon means a concept. Okay, random means it is not decided. We cannot tell which element can give me the radioactivity. Okay, it is a random things which can happen. If the nucleus emits, they decay and they start emitting up some field emissions. Okay, so it doesn't get affected with any of the changes, like any physical change nor a chemical change can affect the chemical change can affect my radioactivity. Clear? Rate of, okay, it does not affect any of my any physical change nor any chemical change. Physical change means neither the pressure or temperature, and chemical change means the the action of the strong electric field or the magnetic field. It does not alter, it will not alter the rate at which it is going to decay, alter the rate of decay of radioactive substances. Yeah. Is it clear? Let me give you the definition, a proper definition of the radioactivity. What is the radioactivity? That radioactivity is a random nuclear phenomenon in which spontaneous emission. How is the emission? The emission is spontaneous of alpha, beta, and gamma radiation from the nuclei of an atom takes place during the decay. There we go. Clear? Now this is going to be the proper definition for the radioactivity. About the radioactivity. Now we are going to learn about their substances. What are the substances? Now this alpha, beta, gamma is only the substances. Okay. So yes, as we have discussed that the radioactivity are the nuclear phenomenon. So we are going to see the changes within the nucleus. Okay, change within the nucleus in what is having we are having is the substances. The substances are the alpha, beta, and gamma. Let's we understand what is the emissions of alpha, beta and gamma, and then later on we will discuss about their properties, and also we will see why we want to learn about it, what is the uses and what are the merits and demerits of it. Okay.
Alpha decay. When a radioactive nucleus disintegrates by emitting an alpha particle, the atomic number decreases by 2 and mass number decreases by 4. The alpha decay can be expressed as follows. Example: radium is converted to radon due to alpha decay. Beta decay. When a radioactive nucleus disintegrates by emitting a beta particle, the atomic number increases by 1 and the mass number remains the same. Beta decay can be expressed as follows. Example: thorium is converted to protoactinium due to beta decay. At a time, either alpha or beta particle is emitted. Both alpha and beta particles are not emitted during a single decay. Gamma decay. When a radioactive nucleus emits gamma rays, only the energy level of the nucleus changes and the atomic number and mass number remains the same. During alpha or beta decay, the daughter nucleus is mostly in the excited state. It comes to ground state with the emission of gamma rays. Example: during the radioactive disintegration of radium into radon, gamma ray of energy 0.187 million electron volt is emitted.
So yes, in our previous video, a minute before, in an animation, we have seen that what is the alpha emission. Okay, how do we come to know that it is an alpha emission? When my parent nucleus, okay, have been reduced by 2 in the atomic numbers. Okay, when there is a reduction in the atomic number, but obviously my element will get changed. Okay, so reduction in the atomic number by 2 and the reduction in the mass number by 4. Okay, give me an element, and it also give me the another element which is as equal to my helium with the 2 atomic number and the 4 atomic mass number. So this is how the alpha emission been recognized. Since the nucleus is unstable, it is going to contain more neutron than the number of protons. So whenever the alpha particles are moving, it is a movement, stream of particles have been moved, which is called as the alpha rays. Okay, so now let me give you some example like uranium with 238 mass, a uranium with atomic number 92 get unstable, okay, and it emits the alpha particles. So while emitting the alpha particle, what is the, here it is given as general formula that A minus 4. So this 238 minus 4 is going to give me 234, which is the thromium. Okay, and down what I have given is that the thromium is not decided on the weight, but about the mass number, as I know, 90. It is going to be a 90th element. So the 90th element is the thromium, plus my another product is going to be helium. Okay, now this is what my example of the alpha emission. Clear? Okay, so now this is the beta emission. In the beta emission, what is happening? My parent nucleus, if you see, this is my daughter nucleus. In the daughter nucleus, what happens? My A doesn't differ. It is as same as, but here my Z get increased by 1. So but obviously this is going to be my next element, where I'm also getting one element. Okay, now this emission is called as the beta particle. Clear? Like how this is called as the alpha particles, the similarly this is called as the beta particle. Clear? So if I show you the example like carbon. Let me take the carbon. Okay, carbon has a mass of 14 and a atomic number as 6. When this get emitted, okay, so what do I get? I get the element of the 7th number, which is the nitrogen, but with the same mass plus my electrons. You see here? So this is considered as a beta particles. Clear? Beta particles, you can see electrons are there. So betas are always negatively charged particles and the alpha are the positively charged particles. Clear? Alphas are positively charged particles, whereas betas are negatively charged particles, and gamma being the neutral ones. Okay, so it will neither have the plus nor the negative. So here this is my gamma emissions, and in this gamma emission what happens, the extra energy is released in the form of electromagnetic radiation, which is called as the gamma rays. Okay, where in this case what happens, the alpha and beta emissions are found to be followed by this gamma. The alpha beta will further turn into the gamma ones. So X, A, Z particles will remain the X, Z, A particles with the extra gamma radiations. This is my parent nucleus, my daughter nucleus. These are the gamma radiations. Clear? Now here there is a star. So what does this star indicates? It indicates the excited state. When the excited state after becoming a alpha and then beta and then the excited state reach to the ground level, what happens? It emits the gamma. Okay, so thus in gamma emission the excited nucleus comes to the ground state. Clear? Now let us see the properties of the alpha, beta, gamma as all three together. If we study it in the differentiation format, what happens? No, it takes us less time to memorize and it becomes easy for us to recollect the things. Okay, in the comparison form if we are studying it. So the first, what is the nature of the alpha, beta and gamma? If I see the nature of the alpha, as I earlier said you, they are the positively charged particles. Yes, so my alpha, they are the positively charged particles, whereas the betas are my negatively charged particles, and gammas are highly energetic electromagnetic radiation. Now they are neither positive nor negative, but they are the electromagnetic radiations, gamma rays. Now in this speed, what is the speed? The speed is 10⁻⁷ meter per second, whereas this is 90% nearer to my light ray. You can see 2.7 into 10⁸ meter per second, and this is the speed as same of my light. Now what is the mass? Mass is 4 times the mass of the proton, which we have already discussed. Okay, 6.68 into 10⁻⁷ kg, and which here the mass is equal to the electrons. Here the mass is equal to the proton. Okay, 4 times the mass of proton, here equal to the mass of electron. Here it has no mass. Okay, here the charges are positive, as we have earlier also studied. Okay, so 2 times that of the proton, and here negative charge particles we are having, and here there is no charge. Clear? So the wavelengths, here we don't have the alpha beta wavelength, but here we have a wavelength for the gammas, since they are the electromagnetic radiation. So we have the wavelength here 10⁻⁻⁴ nanometer or 10⁻⁻13 nanometer. Now the effect of the electric and the magnetic field is less deflected. So yes, deflection, as I said you. Okay, if my atoms get bombarded, okay, my gamma will go and reflected, okay, unaffected to the deflections, okay, it will be undeflected and move in a straight line, whereas my alpha will deflect less since it is heavy weighted, and my beta will deflect more as it is less weighted. Since my alphas are positively charged, they will reflect towards the negative, and since they are negatively charged, beta will move towards the deflect towards the positive. Okay, this is what deflection it is given there. Clear? Next, the ionizing power. Their ionizing power is maximum. Okay, they will ionize maximum is 10,000 times of the gamma, and these are the less than my alpha particles, and these will ionize minimum. Clear? Next, penetrating power range. Penetrating power ranges are small till 3 to the 8 centimeter in air, large up to few meters in air, and here very large up to the few hundred meters in air. This will go deeper than my alpha and beta. Beta will go more deeper than the alpha. Now, stopping substance. How I can stop the alpha? The alpha will get stopped by a thin paper or human skin. Even the alpha will not go inside the flesh. It will stop till skin. Whereas this will go inside the lead or about the 5 millimeter thick aluminum sheets, where this will go even more 30 centimeter thick lead sheets or few meter thick concretes also. Okay, now this is less damage, biological damage. If I see, my alphas are less damage, beta are more, and gamma are immensely damaging the particles. Clear? So these are the properties what we are having with the alpha, beta and gamma. Let us have a summary of the properties in a little animated way.
Different types of radiation rays called alpha, beta, and gamma. Due to the distinct electrical charge characteristics of the alpha, beta, and gamma rays, they can be separated by directing a beam from a radioactive source through a magnetic field. Alpha rays carry particles originating from the nucleus of a radioactive atom. These particles consist of 2 protons and 2 neutrons. Essentially, they are positively charged helium atoms stripped of their electrons. The magnet causes these particles in the alpha ray to bend in one direction. Beta rays are a stream of negatively charged electrons. After passing through the magnet, they bend in the opposite direction of the alpha ray. Because electrons of the beta ray have less mass than the protons and neutrons in the alpha ray, the beta ray undergoes a more pronounced bend. Gamma rays are pure energy. Because a gamma ray has neither mass nor charge, it remains unaffected by the magnetic field. The unique characteristics of these 3 types of radiation affect their capacity to penetrate various materials. Whereas an alpha particle is stopped by a sheet of paper, a beta particle easily passes through paper but is stopped by aluminum. A gamma ray is not impeded by the paper nor aluminum, but its progress can be stopped by lead. The degree to which each of these 3 forms of radiation penetrate human tissue is the basis for limiting a person's exposure to radioactive material. In terms of the impact of radiation on the human body, alpha particles are generally stopped by the outer layer of skin and pose no real harm to underlying tissue. Beta particles, however, are not stopped by the protective layer of skin and can damage deep sensitive tissue. Gamma rays likewise can penetrate deep into the body and cause harm. This is why it is necessary to wear specialized protective gear when working with radioactive materials. When a neutron is fired at high speed into an atom of uranium, it will split the atom in a process called fission. The stability of the nucleus of an atom is maintained by the balance between the repulsive electrical force among protons and the attractive nuclear forces holding the nucleus together. With uranium, this balance is unstable. Thus, when a fast-moving neutron collides with the nucleus of uranium-235, it is stretched into an elongated shape. This elongated shape tips the balance in favor of the repulsive forces, and the uranium-235 atom splits into fragments of krypton and barium. 3 neutrons are also